If you take like a modern high-end desktop computer,
Oh, yeah.
like the kind used for intense 3D rendering or, high-level gaming, and you run it at full capacity, it pulls about 1,200 watts electricity from the wall.
Right, which is just a staggering amount of power.
Yeah. And to put that number into perspective for you listening, that is the exact same amount of power required to run a standard kitchen microwave on high.
Literally the exact same.
So just imagine sitting at your desk, right? Resting your legs against this metal box that contains the continuous electrical fury of a running microwave.
It's a terrifying visual.
And you're just trusting it not to burst into flames or melt into slag or, electrocute you.
Yeah, I mean, it sounds like a horrific workplace safety violation when you frame it that way.
It really does.
But we treat these devices as if they're perfectly sterile, right? Like these silent, magical black boxes. We expect to push a power button, see a screen light up instantly, and just connect to the world. We completely ignore the incredibly violent physical reality happening, like millimeters away from our fingertips.
I think we ignore it because the illusion of perfection is so strong. You look at a smartphone or a sleek aluminum laptop, and it just looks like a solid monolith.
Right, no moving parts visible.
But today, we are shattering that illusion. We're opening up the case. We are going to explore the miniature storms of electricity, the desperate battle against thermodynamics, and the microscopic architecture that keeps the digital world from collapsing under its own weight every single second.
And to guide us through this landscape, we are utilizing a surprisingly rich map. Our source material today is the CompTIA A+ certification guide.
Which is an absolute classic.
It is. Specifically, we're looking at Module 3, which covers installing system devices.
Though to be clear, for you listening right now, we are not treating this like some dry IT manual.
Oh, definitely not.
I'm not interested in just reading a list of part numbers. The mission of this deep dive is to build a vibrant, living mental model of a computer's anatomy. We're stripping away all that corporate jargon to understand the underlying physics. We want to know how the machine actually breathes, thinks, and remembers.
Which means we have to start at the absolute foundation. You cannot process a single piece of data or, render a single pixel without that initial spark of life.
Right.
The journey has to begin with the power supply unit.
The PSU. Okay, let's unpack this because I always picture the power supply as the cardiovascular system of the computer.
That's a great way to look at it.
Because its job isn't just to wildly pump blood, or in this case, electricity into the body. It has to regulate the exact pressure needed for entirely different organs.
Right, it's about precision.
Yeah, if it pumps too aggressively, the brain explodes. If it pumps too weakly, the limbs can't move.
The cardiovascular analogy holds up remarkably well when you look at the raw input, because the electricity coming out of your wall socket is incredibly chaotic.
It's not smooth at all.
Not even a little.
Yeah.
The power grid delivers alternating current, or AC power. And AC is fantastic for traveling long distances from a power plant to your neighborhood because it can be easily stepped up to high voltages for transmission and then stepped down for home use.
Okay.
But the current literally alternates. It reverses direction dozens of times a second.
So it's sloshing back and forth.
Exactly.
I'm assuming a delicate microchip operating on nanoscale logic gates doesn't appreciate its food source constantly changing directions like that.
No, it would be instantly fatal to the chip.
Yeah.
A processor requires a perfectly smooth, unwavering, continuous stream of energy. It needs direct current or DC power.
So it only goes one way.
Right. So the absolute first and most critical function of the PSU is to swallow that roaring, oscillating AC power, tame it, step the voltage down massively, and smooth it out into a flat line of usable DC power.
It's essentially taming lightning in a box.
That's literally what it's doing.
And I noticed in the source material there's a fascinating physical artifact of this process tied to geography.
The voltage switch.
Yeah. Most modern power supplies are auto-switching, meaning they detect the incoming voltage and adjust automatically. But slightly older, or budget models, have this tiny manual red switch on the back.
The infamous voltage selector switch.
It looks so harmless.
It really does, but it's crucial. In North America, the standard wall outlet pushes about 115 to 120 volts. But in much of Europe, Asia, and elsewhere, The grid delivers 230 to 240 volts.
So if I buy an auto switching supply, I can take my desktop from New York to London, plug it in, and the internal circuitry just handles the math.
Seamlessly, yeah.
But if I have that manual red switch, I am suddenly responsible for telling the cardiovascular system what kind of pressure to expect.
And you do not want to get that calculation wrong.
Let's play out the scenario. Say I'm in the US getting 115 volts from the wall, but I accidentally toggle the switch on the back of my PC to 230 volts. What happens when I hit the power button?
In that case, you just experience a mild inconvenience.
Oh, really?
Yeah, because the power supply is bracing itself for a massive influx of 230 volts, but it only receives half of that. The components essentially starve. The system simply won't turn on, and you might spend an hour troubleshooting a black screen before realizing your mistake.
So it's totally harmless.
It is harmless.
That's relief. Let's reverse it. I take my American PC, set to 115 volts, over to a studio in London. I plug it into their 230-volt socket, and I forget to flip the switch.
That is the scenario that engineers refer to as releasing the magic smoke.
Releasing the magic smoke. I've heard that phrase in makerspaces. It implies that electronic parts run on magical, trapped smoke, and once it gets out, the part is dead forever.
It is a dark-humored way of describing a catastrophic electrical overload.
I love that.
If you feed 230 volts into a transformer circuit that is physically calibrated to expect 115 volts, the internal capacitors cannot handle the surge.
They just pop.
Basically, the dielectric materials inside them will instantly break down. You will hear a loud, sharp pop. You will likely see a visible blue spark shoot out of the fan vent, and you will be hit with the distinct acrid smell of burning ozone and melting plastic.
The power supply is just dead.
Best case scenario, the power supply is dead. Worst case scenario, that electrical surge bypasses the safety protections before they can trip, traveling down the cables and permanently incinerating your motherboard, your processor, and your graphics card.
You've essentially detonated a small plasma bomb inside the case.
Yes, you have.
Note to self and to everyone listening. Always verify the voltage, or better yet, just spend the extra $20 on an auto-switching unit.
Highly recommended.
So, assuming we have successfully converted the AC to DC without localized explosions, the power supply now has to distribute that energy. And it doesn't just send one giant wave of electricity everywhere. The source material outlines 3 highly specific direct current voltages: 3.3 volts, 5 volts, and 12 volts.
Going back to your cardiovascular analogy, different organs need different things. The 3.3 volt and 5 volt lines serve as the delicate brain fuel. They provide the incredibly gentle, stable power required for the microscopic logic circuits on the motherboard, the digital signaling, and the memory chips.
The thinking power.
Exactly. Then you have the 12 volt line, which acts as the brute force muscle.
The heavy lifter.
Yeah, the 12 volt current is reserved for heavy lifting. It drives the mechanical motors that spin the physical platters inside older hard drives. It powers the cooling fans. And most importantly, it feeds the massive processing cores on a high-end graphics card or CPU. Those chips need serious wattage to push their computational loads.
And that distribution requires a massive network of wiring. Like if you've ever opened a standard PC case, the power supply just looks like a metallic octopus vomiting a rainbow of cables.
That is a very accurate description.
I want to break down this anatomy, starting with the main artery, the ATX motherboard connector.
The ATX P1 is impossible to miss. It's the widest, thickest cable bundle in the system. Its primary job is to deliver power directly to the motherboard's main circuitry.
Our source mentions a great piece of evolutionary history here. It notes the original ATX connector was a 20-pin block, but modern iterations use a 24-pin block. Sometimes you even see older power supplies utilizing a 20+ 4-pin adapter.
Yeah, the split block.
Why did the motherboard suddenly need 4 extra pins?
It was a direct response to the integration of technology. In the early days, motherboards were fairly barren. If you wanted decent audio, you bought a sound card. If you wanted networking, you bought an Ethernet card.
Right, everything was an expansion.
Exactly. As motherboards started absorbing all these features natively on board, 5.1 surround sound, gigabit networking, a dozen USB ports, the power draw on the board itself skyrocketed.
Oh, that makes sense.
Furthermore, the PCIe slots, which we will get to, needed to deliver up to 75 watts directly through the motherboard traces to expansion cards. The original 20 pins simply couldn't carry that much electrical current safely without the wires overheating.
They'd literally melt.
Right, so rather than completely redesigning a global standard and making old hardware obsolete overnight, engineers brilliantly just snapped an extra 4 pins onto the end of the plastic block.
It's such an elegant retrofit. And if you look closely at those bundles of wires, assuming they aren't covered in black aesthetic sleeving, they are color-coded. I used to think the colors were just random, but they actually function as a visual electrical schematic.
They do. And knowing the code allows a technician to diagnose a failing system with a simple multimeter. Black wires represent the ground. They provide the safe return path for the electrical circuit to complete its loop.
Okay.
Yellow wires are the heavy hitters. They carry the 12-volt muscle. Red wires deliver the 5-volt logic power. And orange wires carry the delicate 3.3-volt signaling power.
So if a system isn't turning on, a technician can take a voltage meter, stick the probes into the yellow and black pins of the ATX connector, and if it reads 10 volts instead of 12, they instantly know the power supply is failing to deliver muscle power.
It isolates the variable immediately. You don't have to guess if the motherboard is dead or the PSU is dying. The wire colors tell you exactly what to test.
Beyond that main 24-pin trunk, the Octopus has other specialized tentacles. We have dedicated CPU power connectors, usually 4 8-pins, located way up at the top left of the motherboard.
Because the processor is the single most power-hungry chip on the board, it eventually outgrew whatever power the 24-pin ATX connector could siphon off to it.
It needed its own feed.
Yeah. The CPU needed its own dedicated, unshared 12-volt pipeline directly from the source to ensure stability during heavy calculations.
Then there are the peripheral connectors, and the one that haunts my memories of building PCs in the 2000s is the 4-pin Molex.
Oh, the Molex. It is a relic of older manufacturing standards. It's a rectangular block of white or translucent plastic housing, 4 large cylindrical pins.
And it was always an absolute nightmare to use. The plastic was incredibly stiff, the pins inside were never perfectly straight, and you had to wiggle and force it with terrifying amounts of pressure to get it to connect to a hard drive. I always felt like I was going to snap the drive in half.
The physical tolerances on Molex connectors were notoriously poor, which is why the industry enthusiastically abandoned them for the SATA power connector.
Thank goodness.
SATA, or Serial Advanced Technology Attachment, utilizes a much sleeker, flat 15-pin blade design. It slides in smoothly, often clicks securely into place, and delivers 3.3, 5, and 12 volts simultaneously to modern solid-state drives and hard disks.
Which leaves the final and currently most controversial set of cables, the PCIe connectors. These come in 6-pin, 8-pin, or the massive new 16-pin variants.
These exist for one primary reason: to feed your graphics processing unit, the GPU. Modern high-end graphics cards are practically supercomputers unto themselves.
Which really are.
They have billions of transistors and their own dedicated banks of memory. While the motherboard slot can provide a baseline 75 watts, a top-tier GPU might demand 450 to 600 watts all on its own.
But why do they need a special 16-pin cable for that? Why not just run a really thick wire from the power supply?
It comes down to fire prevention.
Ah, always a good reason.
If you try to force 600 watts of electrical current through a single standard gauge copper wire, the electrical resistance will cause that wire to heat up like the filament in a toaster. It will melt the plastic insulation and start a fire inside the computer case.
Yikes.
By splitting that massive current across 6, 8, or 16 individual pins and wires, the electrical load is distributed safely.
This brings us directly to the concept of wattage rating. Building a system requires knowing exactly how much total power you need, because you can't just buy the cheapest box on the shelf. The source gives us a baseline. A standard office desktop used for spreadsheets, web browsing, maybe some light media consumption, needs roughly 400 to 500 watts.
That is ample headroom for a CPU with integrated graphics and a solid-state drive. But as you scale up the computational intent, the power demands scale aggressively.
The chart provided in our source is fascinating. If you bump up to an entry-level gaming PC, throwing in a dedicated but modest graphics card like an RTX 4060, the recommendation jumps to 550 watts.
Right.
But if you leap to an enthusiast build, say you are a 3D animator running an RTX 4090 GPU and an enterprise-grade AMD Threadripper CPU, the required wattage skyrockets to 1200 watts or more.
Which brings us back to the microwave analogy. Drawing that much raw power from the wall introduces a massive secondary problem: efficiency.
I think this is a concept a lot of people misunderstand. If my computer requires 600 watts of power to run and I buy a 600-watt power supply, everything is perfectly balanced, right?
That assumption ignores the brutal reality of physics. No electrical conversion process is 100% efficient.
Never.
When the power supply takes the 120-volt AC wall power and transforms it into 12-volt DC power, some of that energy is inevitably lost in the transaction due to the resistance of the internal components.
But the energy doesn't just vanish. The first law of thermodynamics says it has to go somewhere.
What's fascinating here is that it is converted directly into heat. And heat is the absolute arch nemesis of delicate microelectronics.
Right.
Let's use some rough math. If you purchase a very cheap, poorly manufactured power supply that operates at only 60% efficiency, and your high-end gaming system is demanding 600 watts of DC power, that power supply actually has to pull 1,000 watts of AC power from your wall outlet.
So 600 watts makes it to the computer parts.
And a staggering 400 watts is wasted, dissipating as pure thermal radiation right inside the metal chassis of your computer.
You essentially have a 400-watt space heater running constantly next to your heat-sensitive processor. That sounds like a recipe for a total system meltdown.
It is entirely unsustainable, which is why the tech industry introduced the 80 PLUS certification program.
Yeah.
It is an independent verification system that guarantees a power supply operates at a minimum of 80% efficiency across various workloads.
And the program has tiers, named somewhat confusingly after increasingly valuable metals: bronze, silver, gold, platinum, and titanium.
The naming convention is a bit of marketing flair, but the engineering behind it is rigorous. A titanium-rated power supply is mandated to be at least 94% efficient at typical loads.
From a practical standpoint, why should I, the consumer, care? Obviously, my monthly electric bill will be slightly lower because I'm not pulling hundreds of wasted watts from the grid, but is a $10 saving on my electric bill worth spending $100 extra on a titanium PSU?
The electrical savings are just a secondary benefit. The true value lies in thermal management. A highly efficient power supply generates drastically less waste heat.
Which means less cooling needed?
Exactly. Because it runs cooler, the internal fan doesn't have to spin as aggressively, making the entire system significantly quieter. Furthermore, the lower operating temperatures severely extend the lifespan of the capacitors inside the power supply, leading to a much more stable, reliable system over a 5 or 10-year lifespan.
Speaking of keeping things cool and running efficiently, our source points out a physical design choice in PSUs that directly impacts system health: modular versus non-modular cable.
The non-modular power supply is the traditional design. Every single cable, the 24-pin, the CPU cables, the multiple PCIe and SATA tentacles, is permanently soldered into the internal circuit board and exits the metal housing through a single hole.
This means if you are building a relatively simple computer, maybe just one hard drive and no massive graphics card, you still have 6 or 7 thick cables permanently attached that you don't need,
Leaving you with the frustrating task of trying to stuff those extra unused cables into the empty cavities of your computer case. Most people just cram them into a giant knot at the bottom.
which looks terrible through a glass side panel, but more importantly, it creates a physical wall. A giant knot of cables blocks the intake fans from pushing cool room air toward the graphics card and processor. You are strangling the system's ability to breathe.
A modular power supply brilliantly eliminates this issue. The back of the PSU is completely flush, featuring only a grid of empty sockets. You are provided with a separate bag of cables, and you only plug in the specific ones your build requires.
So if I don't have a SATA hard drive, I leave the SATA cable in the box. The inside of the case remains pristine, the air flows unobstructed, and I don't lose my mind trying to route cables.
It is a massive quality of life improvement for builders. Now, before we move away from power delivery entirely, the source outlines one highly specialized iteration of the PSU: redundant power supplies.
This isn't something you'd find in a home gaming rig. This is enterprise-grade technology.
You find these in data centers, hospital networks, and financial server farms. In those environments, a computer unexpectedly turning off is not just an inconvenience.
Right, the disaster.
A dropped server could mean millions of dollars in lost high-frequency trades, or the failure of a life support monitoring system. Uptime must be guaranteed.
So how does a redundant setup guarantee that? Is it just a really tough, oversized power supply?
It's actually multiple, entirely separate power supply modules housed within a single server chassis connecting to a unified backplane. In a standard setup, 2 power supplies might share the electrical load 50-50. But they're usually plugged into entirely different electrical circuits, sometimes even backed by different physical power grids or generators.
Okay, so a rogue backhoe cuts the power line to grid A. one of the power supplies instantly loses wall power.
The moment that happens, the second power supply seamlessly takes over 100% of the load. The transition happens in milliseconds. The server's processor doesn't miss a single clock cycle. It doesn't even register that a catastrophic failure occurred.
That is incredible fault tolerance.
And the true brilliance is that these units are hot swappable. A technician can walk into the server room, identify the dead power module by a red warning LED, unclip it, pull it entirely out of the running server, and slide a replacement module in. The system heals itself without ever being powered down.
It's like performing a heart transplant on a patient while they're running a marathon.
An apt comparison.
That concept of waste heat we explored earlier with PSU efficiency provides the perfect entry point into the next major phase of our journey. We have the power flowing, but the consequence of that power is an immediate, localized inferno. It's time to explore the thermodynamics of tech.
Managing thermal output is arguably the single most defining struggle of modern hardware engineering. The entire layout of a computer is dictated by the need to move heat.
Let's start with the root cause. Why does a computer get hot in the first place? It isn't burning fuel. There is no combustion happening.
The heat is a direct byproduct of electrical resistance. As the direct current from our power supply travels through the microscopic copper traces etched into the motherboard, and specifically as it forces its way through the billions of nanoscale transistors packed into the CPU, it faces physical resistance.
The electrons are literally bumping into the atomic structure of the conductive material.
Exactly. And that atomic-level friction releases kinetic energy in the form of thermal radiation. When you look at a modern central processing unit, you are looking at a silicon chip roughly the size of a postage stamp, containing upward of 10 billion transistors, switching on and off billions of times every single second.
Billions.
The localized heat buildup is intensely concentrated and violently rapid.
If I were to take a high-end processor, place it in a motherboard, plug it in, but neglect to install any cooling system, what is the physical outcome when I hit the power button?
Without thermal throttling fail-safes, the chip would destroy itself in a matter of seconds. The silicon would reach temperatures capable of melting its own internal solder joints before the monitor even had time to display a manufacturer logo.
Just melts itself into a puddle.
Modern chips are heavily armored with software that will aggressively throttle the performance down to a crawl and eventually force a hard thermal shutdown to protect the silicon. But the fundamental law remains. Higher performance computing requires aggressive, dedicated cooling.
The traditional method for achieving this, the standard for decades, relies on air cooling, and the primary component in that system is the heatsink.
The heatsink is an exercise in applied geometry. It is typically a block of highly thermally conductive metal, usually aluminum or copper, that makes direct physical contact with the top of the processor.
But it's never just a solid cube of metal. It's always machined into these complex, bizarre shapes.
Because a solid cube of metal is highly inefficient at dissipating heat into the air, it has very little exposed surface area relative to its mass. To solve this, engineers slice that metal block into dozens or even hundreds of paper-thin vertical fins.
Massive surface area.
Drawing the heat up from the base and spreading it out across all those individual fins, you expose exponentially more of the hot metal to the cooler ambient air, allowing the heat to transfer out of the system much faster.
Now, here is a detail regarding the installation of a heatsink that is absolutely crucial and endlessly fascinating from a physics perspective. You have the flat metal lid of the processor, and you have the flat metal base of the heatsink. You clamp them together with immense pressure. You would assume metal-on-metal contact is the most efficient way to transfer heat.
You would assume that, yeah.
But it's not. You are required to put a dab of thermal paste between them. Why?
Because to the human eye, the machined metal of a CPU lid and a heatsink base appear perfectly smooth, almost like mirrors. But if you were to look at those same surfaces under an electron microscope, the illusion shatters.
It's completely jagged, right?
The metal is heavily pitted, scarred, and uneven. It looks like a jagged mountain range.
The Rocky Mountains of copper and silicon?
Exactly. So when you clamp those two surfaces together, the microscopic mountain peaks touch, but the valleys between them do not. This creates thousands of microscopic pockets of trapped air between the processor and the heatsink.
And air is the enemy here.
Air is a phenomenal thermal insulator. It resists the transfer of heat. It is the exact same principle behind double-paned windows in a house. A trapped layer of air keeps the cold out.
Right.
But in a computer, a layer of trapped air creates a thermal blanket over the processor, preventing the heat from conducting up into the metal fins. the CPU will overheat and crash.
Which is where the paste comes in.
Thermal paste, or thermal compound, is a highly viscous, thermally conductive fluid. It's often suspended with microscopic particles of silver, ceramic, or carbon. You apply a tiny amount, about the size of a grain of rice, to the center of the CPU.
Then you screw the heatsink down.
The mechanical pressure of the mounting hardware forces the paste to spread out, squishing into all of those microscopic valleys, displacing the insulating air and creating a perfect, unbroken thermal bridge between the chip and the cooler.
It's vital, but it's not a permanent fix, is it? I've heard of older laptops suddenly overheating, and the fix is just repasting the CPU.
Because it is a fluid suspension, thermal paste will eventually dry out over a span of several years due to the constant extreme temperature cycles. It hardens, cracks, and introduces air gaps back into the system. Removing the cooler, cleaning off the crusty old paste with high-purity isopropyl alcohol, and applying a fresh drop can drop operating temperatures by 20 degrees instantly.
Okay, so the heat has successfully migrated from the processor, across the paste bridge, and into the metal fins of the heatsink. But it is still radiating inside the computer case. We need to physically eject it, enter the fans.
Right. A heatsink is passive, it holds heat but cannot shed it quickly enough on its own. We attach a high static pressure fan directly to the fins to violently force air through the gaps, constantly stripping the heat away from the metal.
But now we just have a tornado of hot air swirling around inside the chassis, cooking the motherboard and the memory.
This brings us to the science of case airflow. A well-designed computer case operates fundamentally as a wind tunnel. You establish this by carefully orienting case fans. You mount intake fans at the front and bottom of the case. Their sole job is to ingest cool, ambient air from the room.
And then you balance them with exhaust fans.
Positioned at the rear and the very top of the case, leaning into the physical reality that hot air naturally rises. The exhaust fans capture the heat radiating off the internal components and forcefully blast it out the back.
You're orchestrating a continuous flowing river of air. Cool in the front, hot out the back. Which brings us right back to why we hate non-modular power supplies with a giant nest of unused cables.
Exactly. If you have a solid wall of thick cables sitting in the middle of your case, the cool air from the intake fans hits that wall, loses its velocity, and never reaches the processor. Cable management is not about aesthetics. It is about preserving the aerodynamic integrity of the cooling system.
Our source manual includes a very pragmatic warning regarding all this airflow. Dust. Moving massive volumes of air through a box inevitably turns that box into a vacuum cleaner.
Dust is the silent, insidious killer of PC hardware. It gets pulled in through the intake fans and settles over the motherboard traces. More critically, it gets lodged between the tight metal fins of the heat sinks.
Building up a layer of grime that acts just like a winter sweater.
It is highly insulative. A dust-choked heatsink cannot transfer heat to the air. The source manual dictates periodic cleaning using compressed air or a PC-approved vacuum.
I want to highlight that phrase, PC-approved vacuum, because a listener might think, oh great, I'll just grab the nozzle of my heavy-duty shop vac and stick it in there. That is a terrible idea.
It is a phenomenal way to destroy your computer.
Don't do it.
Standard household vacuums rely on friction between the dust particles and the plastic hosing, which generates massive static electrical charges at the nozzle. If you touch a highly charged plastic vacuum nozzle to a microchip on your motherboard, it will discharge a localized lightning bolt, instantly frying the delicate logic gates. Always use canned compressed air or specialized anti-static electronics vacuums.
Good safety tip. Now, air cooling is incredibly reliable, but as we push into the realm of 1200-watt multi-core monsters, blowing air over metal fins sometimes hits a physical wall. The thermal density is just too high. When air isn't enough, we turn to liquid cooling. Specifically, our source details the open-loop liquid cooling system.
Bringing liquid plumbing into the proximity of high-voltage electronics sounds deeply counterintuitive, but the thermodynamic benefits are staggering.
Water and electronics, what could go wrong?
Well, a lot, but liquid, especially specialized chemical coolants, has a profoundly higher specific heat capacity than air. It can absorb and transport massive amounts of thermal energy incredibly quickly.
The first time I saw a complex liquid cooling loop, it immediately reminded me of biology. It looks like the circulatory system of a mammal working to regulate body temperature.
The biomimicry is undeniable. Let's break down the anatomical parts of the loop. You start by removing the bulky metal heatsink from the processor entirely. Instead, you mount a slim metal plate called a water block.
Still using thermal paste, I assume?
Always. But inside this water block, instead of fins reaching up into the air, There is a dense labyrinth of microscopic copper channels.
Like capillaries.
Precisely. Next, you integrate a mechanical pump into the system. The pump acts as the heart, continuously forcing liquid coolant through a network of flexible tubes. The chilled coolant rushes into the water block, weaves through the microchannels, absorbs the intense heat directly from the silicon, and gets pumped out the other side.
So the heat is instantly carried far away from the delicate processor, but the liquid is now boiling hot. How do you cool the liquid down?
So tubing carries the hot liquid to a radiator, which is usually bolted to the outer edges of the computer case.
Oh, like in a car.
Just like a car. The radiator is essentially a massive, spread-out heat sink. The hot liquid winds through thin tubes inside the radiator, transferring its thermal energy to an enormous grid of metal fins. Large, slow-spinning fans then push the cool room air through the radiator to dissipate the heat.
Mimicking the biological act of sweating. You move the heat to the surface of the skin to be expelled, while the newly chilled blood or coolant flows back to the core to start the cycle again.
It is hyper-efficient. And because the radiator fans can be large and spin slowly, it is often much quieter than a small air cooler screaming at maximum RPM.
But reading the source materials maintenance checklist for an open-loop system proves this is high-performance sports car territory. It demands constant vigilance. You can't just build it and ignore it.
An open-loop system introduces multiple single points of catastrophic failure. The source lists 4 mandatory maintenance checks. First, meticulous leak testing.
Right.
A cracked acrylic tube or a slightly loose compression fitting will drip highly conductive fluid directly onto your $1,000 graphics card, destroying it instantly.
Terrifying. Second on the list is cleaning the radiator, which makes sense. Dust clogs a radiator just like an air cooler. Third is monitoring temperatures.
Because if the mechanical pump suffers a failure, the liquid stops flowing. It just sits in the water block above the processor and begins to boil. The CPU will rapidly overheat and shut down.
And the fourth maintenance task is perhaps the most surprising. Periodically draining and replacing the coolant fluid itself. Does the water go bad?
The physical environment inside the loop is harsh. The continuous temperature swings break down the anti-corrosive chemicals in the coolant. Furthermore, if you accidentally mix metals in your loop, say a copper water block with an aluminum radiator, the liquid acts as an electrolyte, triggering galvanic corrosion that will literally eat away the metal blocks from the inside out.
Not to mention the biological threat.
Yes. Warm water combined with light from case LEDs is a perfect breeding ground for microscopic algae and bacteria. If you do not use proper biocides, your loop will grow a layer of green slime that clogs the microchannels in the CPU block, ruining the system's ability to absorb heat.
So you get unparalleled performance, but you have to become a part-time plumber, chemist, and biologist to maintain it.
It is the ultimate expression of enthusiast computing.
Let's synthesize where we are in our mental build. We have a robust, highly efficient PSU providing stable DC voltage. We have implemented aggressive thermodynamic infrastructure to constantly wick away the devastating heat of electrical resistance. The machine has power and it is stable. The CPU is awake and ready to compute.
But it needs something to work on.
Exactly. To actually do anything useful, it requires a workspace. It needs somewhere to put the data it's actively working on, which brings us to the third major pillar, the brain's workbench, system memory.
Universally referred to as RAM, random access memory.
Before we dive into the deep architecture of RAM, we have to address the most common misconception in consumer technology. People constantly confuse memory with storage.
Constantly.
They will say, my laptop is running so slowly, I must be out of memory. But what they actually mean is they've downloaded too many movies and their hard drive is full.
It is an incredibly pervasive confusion, primarily because operating systems historically reported both capacities in megabytes or gigabytes.
I find the best way to untangle them is to use a kitchen analogy. Think of the processor, the CPU, as a Michelin star master chef.
Okay.
The chef is impossibly fast and highly skilled, capable of dicing ingredients in a microsecond. But the chef needs a place to actually prepare the meal. System memory, RAM, is the stainless steel countertop situated immediately in front of the chef. It is the active high-speed workspace. The hard drive, the storage, is the deep freeze down in the basement of the restaurant.
I like this framework. It perfectly captures the latency difference.
When you double-click a program icon, like opening a massive Photoshop file, the computer essentially sends a runner down to the deep freeze in the basement, grabs the heavy ingredients, hauls them upstairs, and places them onto the RAM countertop. Now the CPU chef can interact with them instantly.
And the most defining technological characteristic of that RAM countertop is that it is volatile memory.
Volatile meaning unstable.
Volatile, meaning it physically requires a continuous, uninterrupted supply of electrical power to maintain its state. To understand why, we have to look at the microscopic architecture. RAM stores data. The ones and zeros inside billions of microscopic cells, each consisting of a transistor and a capacitor.
Capacitor is like a tiny battery.
Precisely. If the capacitor holds an electrical charge, the computer reads it as a 1. If it is empty, it reads a 0. But capacitors are fundamentally imperfect containers. They naturally leak their electrical charge over time.
Like a bucket with a microscopic hole on the bottom.
Yes. So, to prevent the data from fading away into meaningless noise, the memory controller must continuously send a refresh signal, literally thousands of times every single second, to read the state of every capacitor and top off the charge in the ones that hold a 1.
And what happens if the power supply shuts off, or you accidentally kick the power cord out of the wall?
The refresh signal stops instantly. Within fractions of a second, every single charged capacitor drains to 0. The entire contents of the RAM countertop evaporate into total nothingness.
Which is the painful physical reality behind losing a 10-page essay because you hadn't clicked save before a power outage. The chef dropped all the ingredients on the counter and fled the building, and everything was lost.
Exactly. Now, if we want to measure just how fast this system can operate, the source material breaks down the architecture into two distinct pathways: the address pathway and the data pathway.
Returning to our kitchen, how do these pathways dictate the chef's workflow? What is the address pathway?
The address pathway, or address bus, dictates the total number of unique memory locations the CPU is capable of physically tracking. In your analogy, this represents the physical square footage of the countertop. How many distinct cutting boards can the chef fit on the table at one time?
If you have a small address pathway, you have a tiny counter. The chef might be incredibly fast, but they can only work on 2 carrots at a time.
Historically, this was a massive bottleneck. Older 32-bit processors had an address pathway that mathematically maxed out at roughly 4 billion locations, meaning the computer could only ever utilize 4 gigabytes of RAM, no matter how much you physically installed. The shift to 64-bit processors exponentially increased the size of the address pathway, essentially giving us an infinitely large countertop for modern computing.
That covers the size of the workspace. So what is the data pathway?
The data pathway determines the volume of actual information that can be transferred between the RAM and the CPU during a single clock cycle. This is the width of the door between the chef and the counter, or how large the chef's hands are. A wider data pathway means the processor can scoop up massive handfuls of data simultaneously, rather than painstakingly picking it up one bite at a time.
A massive counter and a chef with giant, lightning-fast hands. That is the goal of hardware engineering. Which leads us to a brief history of memory timing, because making the RAM fast enough to keep up with the CPU required some truly brilliant problem solving.
The source outlines the lead from older asynchronous DRAM to SDRAM in 1993. The S stands for synchronous.
Because before 1993, the memory and the processor were completely out of sync.
Completely. The older RAM operated on its own internal timing. The ultra-fast CPU would send a request for data down to the RAM, and then the CPU would literally just sit there, idling in a wait state, burning power and doing nothing until the RAM eventually got around to serving up the data. It was catastrophically inefficient.
Like the chef screaming for a knife, but the sous chef is just casually walking across the room at their own pace.
SDRAM fixed this by tethering the memory's operations directly to the motherboard's system clock.
The system clock acting like a metronome for the entire computer. Tick-tock, tick-tock.
With SDRAM, the memory operations were locked into that rhythm. The RAM knew exactly when the CPU was going to ask for data, and it had it ready on the exact tick of the metronome.
But the relentless demand for more speed meant even perfect synchronization wasn't enough. In 1996, the industry introduced a technology that I consider one of the most elegant engineering cheats in computing history: DDIR SDRAM, double data rate.
If we connect this to the bigger picture, it is a phenomenal example of lateral thinking in engineering. The traditional brute force method to make a computer faster is to increase the frequency of the system clock, make the metronome tick faster.
Sure.
But as we discussed regarding thermodynamics, faster clock speeds generate immense unmanageable heat. You hit a physical wall.
You can't just make it tick faster without melting the board, so how do you move more data?
You look closer at the shape of the clock signal itself. An electrical clock cycle isn't just a dot on a timeline. It is a square wave on an oscilloscope. It has a rising edge, the voltage goes up, it stays high for a moment, and then it has a falling edge. The voltage drops back down. Standard SDRAM only transmitted a package of data on the rising edge of the wave, the tick.
Meaning the falling edge, the talk, was just dead air, wasted potential.
The engineers behind DDR figured out how to trigger the memory chips to transmit a package of data on the rising edge, and a second package of data on the falling edge of that exact same clock cycle.
They utilized the tick and the tock.
They instantaneously doubled the total throughput of the memory, doubling the bandwidth of the entire system without having to increase the underlying clock frequency by a single hertz. They got twice the speed with zero extra heat.
It is brilliant, and that foundational concept still governs the RAM we buy today. The source tracks the generations, DDR2, DDR3, DDR4, and the current cutting-edge standard, DDR5.
With each subsequent generation, manufacturers refine the internal architecture. They dramatically increase the density of the memory chips, and critically, they lower the operating voltage, which reduces power consumption and ambient heat.
Now, a massive blinking warning light for anyone listening who wants to upgrade their computer's memory. If you own a PC built 4 years ago, it likely uses DDR4. If you walk into a store today and buy the newest, fastest, incredibly expensive DDR5 memory sticks, you are in for a terrible surprise.
You cannot mix and match DDR generations. They are electrically and physically incompatible.
If I try to shove a DDR5 stick into a DDR4 motherboard slot, will it work?
It won't even fit. Hardware designers purposefully alter the physical layout of the memory module for every generation. There's a small notch cut into the bottom edge of the RAM stick where the gold connector pins are. The position of that notch moves slightly with every iteration.
It's a physical, idiot-proof failsafe.
It is absolutely necessary, because a DDR4 module might require 1.2 volts to operate, while a DDR3 module required 1.5 volts. If you could physically force an older stick into a newer motherboard, the voltage mismatch would immediately permanently fry the memory controller. The physical notch prevents catastrophic user error.
So, assuming we have the correct generation of RAM, the source outlines a few methods to maximize the performance of our countertop. The main one being channel configurations: single, dual, and quad channel.
This goes back to our data pathway, the width of the door between the chef and the counter. In a single-channel configuration, the processor has one 64-bit wide avenue to access the memory.
One door.
But modern motherboards have multiple memory slots. If you take two identical sticks of RAM matched in speed and capacity and install them into specific color-coded slots, the motherboard's memory controller activates dual-channel mode.
It essentially opens a second door.
It binds those two separate physical sticks into a single logical block of memory and utilizes two separate 64-bit pathways simultaneously. You have doubled the total data bandwidth instantly. High-end workstation motherboards support quad-channel memory, utilizing 4 synchronized sticks to provide massive data pipelines for tasks like real-time 8K video editing.
There is one more highly specialized feature of RAM mentioned in the outline, usually represented by an acronym at the end of a very expensive price tag: ECC, Error Correcting Code.
To understand ECC, you have to accept a terrifying reality about computers. They make mistakes constantly.
We think of them as flawless math machines.
But they exist in the real physical world. We discussed how RAM holds data as microscopic electrical charges and capacitors. Those charges are vulnerable to physical interference. A spike in thermal radiation, a slight fluctuation in the power supply voltage, or even high-energy cosmic rays originating from outside our solar system can strike a silicon chip.
Wait, cosmic rays, we are blaming computer errors on literal outer space.
It is a documented phenomenon called a single event upset. A highly energized particle strikes the silicon, carrying just enough energy to physically flip the electrical state of a single capacitor. It changes a 0 into a 1.
A bit flip? What are the actual consequences of a single bit flipping out of billions?
It depends entirely on what that bit represented. If that bit was dictating the color of a single pixel in a video game skybox, you might see a tiny blue dot flash red for a microsecond. You would never notice. But if that bit was a crucial piece of mathematical logic in the operating system's kernel,
the whole system crashes, the blue screen of death.
Instantaneous fatal error. For a home user, a random reboot once a year is just an annoyance. But imagine a server farm executing millions of high-frequency stock trades per second, or a hospital server managing patient medication databases. A bit flip causing a server to crash, or silently corrupting a data point, could cost millions of dollars or threaten lives.
Enter ECC memory.
ECC RAM includes an additional dedicated microchip right on the memory module. As data flows in and out, this chip performs highly complex real-time mathematical parity checks. If a cosmic ray or a thermal anomaly flips a bit, the ECC chip instantly detects that the math no longer balances.
It knows an error occurred. Can it fix it?
It can, By reverse engineering the parity algorithm, it mathematically deduces exactly which bit was flipped, corrects it back to its original state on the fly, and allows the system to continue operating without ever crashing.
It's an invisible safety net. Why isn't it standard in every laptop and gaming PC?
Cost and speed. The extra silicon makes ECC modules significantly more expensive, and the requirement to constantly perform complex math on every piece of data introduces a slight latency delay. For consumer performance, speed is prioritized over absolute perfection. For enterprise servers, flawless stability is the only metric that matters.
Okay, one final scenario for our RAM section. Let's push the system to the breaking point. The chef is overwhelmed. You have 40 tabs open in Google Chrome, you're rendering a 4K video in the background, and you're running a massive spreadsheet. You completely fill the physical RAM, the countertop is 100% full. What happens? Does the computer just freeze and die?
The computer attempts a desperate survival tactic known as virtual memory. When the operating system realizes it has zero physical RAM left, it looks down into the basement at the hard drive. It carves out a chunk of storage space and says, in an emergency, I'm going to pretend this slow storage space is actually fast memory.
So the chef has run out of counter space and starts putting ingredients on the floor.
Yes. The system takes data that you haven't interacted with in a few minutes, maybe a minimized web browser tab, and physically moves it from the fast RAM down to the slow hard drives to clear up space on the counter for whatever you are currently clicking on. This process is called paging or swapping.
And picking things up off the floor is obviously much slower than grabbing them off the counter.
Exponentially slower. We are talking about the difference between nanoseconds and milliseconds. If your computer suddenly grinds to an agonizing halt, where moving the mouse stutters and clicking a folder takes 30 seconds to register, it's almost always because you have exhausted your physical RAM.
The system is just furiously moving data back and forth between the RAM and the hard drive, completely consumed by the logistics of just trying to stay alive. Thrashing.
Thrashing is the exact technical term. The only permanent solution is to close applications or physically install more RAM to buy a bigger countertop.
Which provides a seamless transition into our final hardware frontier. We just highlighted how the hard drive acts as the deep freeze, the permanent repository. We have a cooled CPU, and we have a lightning-fast, volatile workspace. But the moment the power supply clicks off, the RAM is wiped clean. We need a vault that survives the darkness. Section 4. Storage devices and data redundancy.
And here we wade into the most significant, transformative paradigm shift in consumer computing of the last 2 decades. The great debate between the hard disk drive, the HDD, and the solid-state drive, the SSD.
Let's establish the baseline by examining the old guard first, the hard disk drive.
The mechanical HDD is a marvel of microscopic engineering, but its fatal flaw is right there in the name. It's mechanical. If you pry open the heavy metal casing, you find highly polished, perfectly circular platters, usually made of glass or aluminum, coated in a specialized magnetic substrate.
They look exactly like miniature CDs or record albums.
And they operate on the exact same physical principle. An electric motor spins these platters at terrifying speeds, typically 5,400 or 7,200 revolutions per minute.
So the platter is spinning at over 100 miles an hour at the outer edge.
Hovering above these blurring platters is an actuator arm. At the very tip of this arm is a microscopic read-write head. As the platter spins, the arm sweeps back and forth violently across the surface. The head uses an electromagnetic pulse to alter the magnetic polarity of tiny microscopic regions on the platter, encoding a 1 or a 0.
And you said the head is hovering. It doesn't actually touch the glass platter, right? Like a needle on a record player.
If the head touched the platter while it was spinning at 7,200 RPM, it would violently gouge the magnetic material, instantly destroying the data. The head is designed to generate aerodynamic lift, flying on a microscopic cushion of air generated by the spinning disk. It flies just a few nanometers above the surface. To put that scale in perspective, the gap between the flying head and the spinning data is significantly smaller than the width of a human hair, or even a single particle of smoke.
That sounds incredibly terrifyingly fragile.
It is inherently fragile. If you accidentally drop a spinning hard drive or knock your laptop off the table, the mechanical shock will overcome the aerodynamic lift. The metal head will violently slam into the glass platter. This is known as a head crash, and it usually results in the immediate, permanent death of the drive.
I remember the sound of a failing hard drive, that rhythmic clicking noise, the click of death.
That is the sound of the mechanical arm failing to find its tracking data, slamming into its physical bump stop, resetting, and trying again. Click, click, click.
Enter the modern savior of laptops everywhere, the solid-state drive. The SSD.
The SSD completely fundamentally changes the architecture of storage by eliminating all moving parts. There's no motor, no spinning platter, no flying arm. If you open an SSD, it is completely silent. It is just a flat fiberglass circuit board populated with small black squares of NAND flash memory chips.
It's the exact same technology used in a USB thumb drive or the SD card in your digital camera, just scaled up massively for capacity and speed.
Exactly. Data is written electrically, trapping electrons inside microscopic floating gate transistors to represent the ones and O's.
I want to highlight a specific emphasized note from our CompTIA outline here because it explicitly debunks a lingering misconception. The text points out the myth that SSDs can sometimes underperform compared to HDDs and firmly states, not true.
It is a myth that refuses to die, largely born from the very early, unrefined days of flash memory. Today, for any consumer or workstation application, an SSD will absolutely obliterate a mechanical HDD in performance metrics.
And the reason goes back to the physical mechanics we just discussed, right? The seek time.
Precisely. If you ask a mechanical hard drive to open a large file, the drive has to wait for the platter to physically spin around so the correct sector is under the head, and has to wait for the mechanical arm to physically swing across the disk. This physical movement takes milliseconds. In computing terms, a millisecond is an eternity.
But an SSD doesn't have to move anything.
An SSD has near zero seat time. The memory controller just sends an electrical signal down a copper trace directly to the correct memory cell. The data is accessed at near the speed of light. It is instantaneous.
This is the exact technological difference between an old PC that takes 3 agonizing minutes to boot up Windows and a modern PC that boots to the desktop in 8 seconds.
It fundamentally changes how responsive a computer feels. Furthermore, because there are no delicate moving parts, an SSD is incredibly durable. You can drop an SSD down a flight of stairs while it is reading data, and it will likely be perfectly fine.
So SSDs are exponentially faster, completely silent, and physically indestructible compared to spinning glass, which begs a very obvious question. Why does the source outline have a section titled "Where HDDs May Still Have an Edge"? Why are factories still producing millions of mechanical hard drives every year if the technology is obsolete?
Because in enterprise environments, the technology is far from obsolete. HDDs still dominate in 2 crucial arenas: cost per gigabyte at massive scales and the physics of archival data recovery.
Here's where it gets really interesting. Let's break those down. Cost first.
Manufacturing dense NAND flash memory chips requires multi-billion-dollar fabrication plants and incredibly complex silicon wafer processing. While prices have fallen dramatically, SSDs are still a premium product. To put it in perspective, for the exact same amount of money you would spend on a high-performance 2 terabyte SSD, you can purchase a massive 10 or 12 terabyte mechanical hard drive.
You get 5 to 6 times the total storage capacity for the same budget.
If you are building a home gaming PC, you want the 2 terabyte SSD for fast load times. But imagine you are managing a data center for a hospital, archiving millions of high-resolution patient x-rays, or you are running a server farm holding petabytes of security camera footage. You don't care if a file takes 5 extra milliseconds to open. You just need an impossibly vast, cheap bucket to dump data into. The mechanical HDD is still the undisputed king of cheap, deep storage.
That makes perfect economic sense. But let's look at the second point, because this one genuinely caught me off guard. The outline states regarding archiving: data can possibly be extracted from dead HDDs, but not SSDs. You are telling me the fragile spinning glass disk that dies if you bump it is actually safer for long-term data preservation than the tough, non-moving silicon chip?
It is one of the most brutal paradoxes in IT engineering. To understand it, we have to look at the physics of how these drives fail. When a mechanical HDD dies, it is almost always a mechanical failure. The motor seizes up, or the actuator arm snaps, or the circuit board shorts out.
But the physical glass platters inside, the magnetic substrate actually holding the ones and nullities.
The platters are usually perfectly intact, trapped inside the dead metal box. The data is still there. The drive just lacks the physical ability to read it. If that data is priceless, say a decade of irreplaceable family photos or a corporation's tax records, you can send that dead drive to a specialized data recovery laboratory.
And what do?
In a hermetically sealed clean room, technicians wearing biohazard-style suits will crack open the dead drive casing. They carefully mechanically lift the magnetic platters out, place them into a highly specialized donor drive assembly, and use specialized software to manually scrape the magnetic data off the disks. It can cost thousands of dollars, but the physical reality allows for the possibility of rescue.
Okay, now let's apply that catastrophic failure to an SSD.
When an SSD dies unexpectedly, it is rarely physical damage. It is almost always an electrical failure of the main controller chip, or a sudden power surge that arcs through the NAND flash memory array. When an electrical surge hits microscopic silicon transistors, it physically alters them. It melts the gates.
So there is no platter to rescue.
The data is not magnetically stored on a physical medium you can extract. It is trapped in microscopic electrical states. When the silicon burns out, the data is instantly, permanently vaporized. No amount of money, no specialized clean room, and no forensic software can recover data from a fried NAND chip. It is gone forever.
That is chilling. The CompTIA outline actually bolded this warning. You should not keep your only backups on SSDs. When the drive is dead, the data is gone.
It is a foundational rule of data management. You use SSDs for your operating system, your applications, and your active daily projects because they provide incredible speed and efficiency. But your permanent, deep-time archives, your ultimate backups, should live on mechanical hard drives because mechanical failures can be circumvented. Electrical vaporization cannot.
But even armed with that knowledge, relying on a single hard drive for your business seems like playing Russian roulette. All hard drives, mechanical or solid state, have a 100% mortality rate. They will all eventually die.
Which brings us to the ultimate fail-safe mechanism, a technology designed specifically to defeat hardware failure. RAID.
RAID, the redundant array of independent disks.
Historically, it stood for Redundant Array of Inexpensive Disks, born from an era when massive single drives were too costly, so engineers figured out how to chain a bunch of cheap, small drives together. The premise of RAID is taking multiple, physically separate hard drives and using a specialized hardware controller or software to trick the operating system into thinking they're just one single, massive drive. The controller that manages how data is distributed across the physical disks to provide either blistering speed or incredible safety.
The outline provides a breakdown of different RAID levels. Let's walk through the architecture of these configurations, starting with RAID 0.
RAID 0 is known as striping.
Yeah.
Imagine you have two 1 terabyte drives and you want to save a massive 2 gigabyte video file. The RAID controller mathematically chops that video file into tiny uniform blocks. It writes block 1 to drive A, block 2 to drive B, block 3 to drive A, and so on.
Distributing the workload, why is this beneficial?
Because when you want to open that video file later, the computer doesn't have to wait for one drive to do all the work. Drive A reads its half of the file at the exact same time drive B reads its half. They blast the data back to the processor simultaneously, effectively doubling your read and write speeds. You get the combined capacity 2 terabytes and double the performance.
That sounds amazing. What is the catch? Because in computing, there is always a trade-off.
The catch is that the word redundant in the RAID acronym does not apply to RAID 0. There is absolutely zero fault tolerance.
If one drive dies.
If drive A suffers a mechanical failure, you don't just lose half of your video. Because the file was striped sequentially across both drives, missing every alternating block corrupts the entire file. In fact, it corrupts the entire file system. If one single drive in a RAID 0 RAID dies, every single piece of data across all the drives is instantly and permanently destroyed.
Maximum speed, maximum danger. It's the sports car with no seatbelts.
It is heavily utilized by video editors as a temporary scratch disk for processing high-resolution footage quickly, but they never store permanent data on it.
Okay, what is the exact opposite of that? The safest possible configuration?
That would be RAID 1, known as mirroring. The architecture is exactly what it sounds like. You install 2 hard drives. Every single time you save a file or modify a document, the RAID controller writes it to drive A and simultaneously writes an exact, bit-for-bit duplicate clone to drive B.
An invisible real-time backup.
Total redundancy. If drive A catches fire, the computer doesn't crash. It doesn't even display an error message interrupting your work. It seamlessly continues operating solely off drive B, while quietly alerting you to replace the burnt drive. Once you slide a new drive in, the controller automatically rebuilds the mirror in the background.
But the trade-off here is the wallet.
Yes. You purchase 2 expensive 4 terabyte hard drives, but you only receive 4 terabytes of usable storage space. You sacrifice 50% of your raw capacity to achieve that peace of mind.
So RAID 0 is incredibly fast but suicidal, and RAID 1 is perfectly safe but economically inefficient. There must be a middle ground.
For decades, the undisputed king of the enterprise server room has been the middle ground. RAID 5. Striping with parity.
To build a RAID 5, you need a minimum of 3 hard drives. The source says it uses distributed parity across all disks. One disk can fail, and data is reconstructed. I want to really dig into this because how can a computer reconstruct data that lived on a drive that is currently sitting dead in a dumpster?
It feels like dark magic, but it is actually just a brilliant application of basic algebra, specifically XOR logic gating. Let's use a heavily simplified analogy using basic addition to visualize the math. Imagine we have our three drives, drive A, drive B, and drive C.
Okay, 3 empty drives.
The computer wants to save some data represented by the numbers 3 and 7. To get the speed benefits of striping, it writes the number 3 onto drive A. It writes the number 7 onto drive B.
Data is striped. But where is the safety?
Before the controller finishes the operation, it pauses and runs a mathematical parity calculation. It looks at the data and says 3 plus 7 equals 10. It then takes that answer, the number 10, and writes it onto drive C. That number 10 is the parity data.
So drive A holds a 3, drive B holds a 7, and drive C holds the parity answer 10.
Now, a catastrophic power surge hits the server, and drive B completely dies. It is dead metal. The drive containing the number 7 is gone. How does the system survive?
The RAID controller knows that drive A holds the number 3, and it knows that drive C, the parity drive, holds the final answer, 10.
Exactly. The controller simply runs the algebra in reverse. It knows the formula is A plus B equals C. It plugs in the surviving numbers. 3 plus missing data equal 10. The processor instantly, mathematically determines that the missing data on the dead drive must have been a 7.
It calculates the ghost of the dead drive.
It reconstructs the missing data on the fly, feeding it to the user as if nothing happened. In a real-world RAID 5, it distributes this parity data dynamically across all three drives to prevent a bottleneck. But the algebraic principle remains. You get the massive speed boost of striping, you get excellent capacity, you only lose the equivalent of one drive's worth of space to store the parity math, and you can survive any single drive failure.
It's an incredibly elegant solution. But what happens if the server gets incredibly unlucky and 2 drives die simultaneously?
Then the algebra breaks down. If you lose drive A and drive B, you lose the 3 and the 7. Just knowing the parity answer is 10 doesn't help you because the missing numbers could be 5 and 5 or 8 and 2. The data is permanently lost. If a business demands survival against multiple simultaneous drive failures, they must escalate to RAID 6.
Striping with dual parity.
RAID 6 requires a minimum of 4 hard drives. It performs the striping, but it runs 2 completely different, highly complex mathematical algorithms on every block of data, generating 2 distinct sets of parity. You lose 2 drives worth of raw capacity to the math, but you can undo the simultaneous death of 2 physical hard drives without losing a single byte of data.
The outline does flag a significant performance drawback to RAID 6, noting slower write performance due to the extra math required.
Because the RAID controller chip has to solve 2 complex cryptographic equations every single time a user hits save, it introduces latency. It is an impenetrable vault, but the heavy steel doors take time to swing shut.
Which brings us to the ultimate, uncompromising solution for those with unlimited budgets. The nested architectures, RAID 10.
Or RAID 1 plus 0. This is the configuration for a database admin who demands the blazing speed of RAID 0, the absolute rock-solid safety of RAID 1, and who does not care how much hardware it requires to achieve it.
Walk me through the physical build of a RAID 10.
You start with a minimum of 4 hard drives. First, you take drive A and drive B, and you configure them as a RAID 1 mirror. They are identical, redundant twins. Then, you take drive C and drive D, and you configure them as a second, entirely separate RAID 1 mirror.
So you have 2 distinct clusters, and each cluster is perfectly safe from a drive failure.
Yes. Finally, you take those 2 mirrored clusters and you apply a RAID 0 stripe across them. When the server needs to write a massive database file, it splits the file in half for speed. It throws the first half at cluster 1, which instantly duplicates it to 2 drives. It throws the second half to cluster 2, which duplicates it.
You are striping across mirrors.
You achieve tremendous read and write speeds, and the fault tolerance is staggering. You can lose 1 drive in the first mirror and simultaneously lose 1 drive in the second mirror, and the array keeps running at full speed. It is the gold standard for high-performance enterprise storage, but it requires sacrificing exactly 50% of your total raw drive investment.
It perfectly illustrates the golden rule of hardware engineering: speed, capacity, safety, cost. You are allowed to pick 2, maybe 3, but you can never have all 4.
It is the inescapable compromise of physical constraints.
Before we finalize our deep dive into storage, the source material briefly catalogs a few alternative storage mediums that exist outside the main PC chassis: removable enclosures, flash memory cards, and optical drives.
Removable enclosures are a brilliant utility. They allow you to take the internal SATA hard drives or SSDs we've just discussed, place them inside a protective aluminum or plastic shell, attach a small controller board, and plug them externally into a laptop via USB or Thunderbolt cable. It turns a fragile internal organ into a ruggedized portable vault.
Then we have flash and SD, secure digital cards.
They utilize the exact same non-volatile NAND flash memory cells as a high-end SSD, but the engineering focus is extreme miniaturization for devices like smartphones, drones, and digital cameras.
I always get confused buying SD cards because there's so many cryptic symbols on them. U1, V30, Class 10.
Those symbols represent guaranteed sustained write speeds. You can buy a very cheap high-capacity SD card to store MP3 audio files, and it works perfectly. But if you try to put that same cheap card into a professional 4K video camera, the camera will crash because the slow flash memory physically cannot ingest the massive wave of video data fast enough. The symbols ensure you are buying a card with a data pathway wide enough for your specific hardware.
And finally, the technology that feels like a nostalgic relic but still holds a vital place in certain industries: optical drives, the CD, the DVD, and the Blu-ray.
Optical media is fascinating because it abandons magnetic fields and trapped electrons entirely. It relies on physical topography and the behavior of light.
How does a laser beam read a movie off a piece of plastic?
During manufacturing, a high-precision press stamps billions of microscopic physical divots, called pits, into a layer of reflective polycarbonate. The flat areas between the pits are called lands. Inside the optical drive, a highly focused laser beam shines onto the spinning disk. When the laser hits a flat land, the light reflects perfectly straight back into an optical sensor. The computer registers a 1, but when the laser hits a pit, the light scatters and misses the sensor. The computer registers a 0.
You are literally reading binary code with a laser beam tracking across microscopic craters.
It is incredibly precise. And the format evolutions, from CD to DVD to Blu-ray, were achieved primarily by changing the wavelength or color of the laser. A Blu-ray drive uses a blue-violet laser, which has a much tighter wavelength than the red laser in a DVD drive. This allows the laser to read much smaller pits, meaning you can pack exponentially more data onto the exact same physical size of the plastic disc.
And what about burning your own discs? The CDRs and the rewritable formats. You aren't physically stamping plastic in your desktop drive.
No, consumer drives use chemical trickery. A recordable disc, a CDR, replaces the stamped plastic with a layer of photosensitive organic dye. The laser in the drive powers up to a higher intensity and literally scorches the dye, turning it dark and opaque. The dark spot scatters the reading laser later, simulating a physical pit.
But you can only burn it once.
Exactly, the chemical change is permanent. A rewritable disc, however, utilizes a specialized phase-change metal alloy. A medium-power laser pulse can melt the alloy into a dark, non-reflective state. But a completely different lower-temperature laser pulse can actually recrystallize the alloy, resetting it back to a reflective surface. It allows you to erase and rewrite the data thousands of times by manipulating the physical state of the metal with light.
That is just phenomenal engineering. So, what does this all mean? We have covered a tremendous expanse of technical territory today. Let's take a moment to step back and survey the machine we build in our minds.
We have meticulously constructed a complex, thriving digital ecosystem.
We started by harnessing raw, chaotic energy at the wall socket. We observed the PSU taming that AC power, stepping it down through precise transformers, and distributing distinct, vital DC voltages to the specialized organs of the system. We confronted the harsh realities of thermodynamics, recognizing that incredible computational power generates devastating heat. We mapped the intricate defensive structures, the microscopic thermal bridges, the carefully orchestrated wind tunnels, and the biomimetic liquid cooling loops designed to expel that heat before the silicon destroys itself.
From there, we established the workbench. We watched the processor synchronize with the DDR RAM, manipulating the rising and falling edges of a clock signal to shuttle data in and out of microscopic, power-hungry capacitors fast enough to sustain the illusion of instantaneous thought. We explored the vulnerabilities of that memory to something as wild as a cosmic ray, and how ECC algorithms catch those errors in the dark.
And finally, we engineered the permanent vaults. We debated the physics of storage, contrasting the blistering speed and electrical fragility of the solid-state drive against the cheap, massive, mechanically vulnerable spinning platters of the hard disk drive. We explored the mathematical fortresses of RAID arrays, utilizing algebraic parity to cheat physical hardware death, and we looked at how lasers read topography to store data on plastic. So for you, the listener, why have we spent the last hour pulling apart the anatomy of a computer? I think it's because it shifts your perspective. Tomorrow, when you sit down at your desk, push a plastic power button and wait a few seconds to check your email or load up a high-definition video. I want you to look past the sleek, silent aluminum case. I want you to visualize the beautiful, controlled chaos happening inside. It isn't magic. It is a violent, meticulously orchestrated symphony of physics, thermodynamics, chemistry, and mathematics, executing billions of times a single second, all just to serve you that experience.
It represents the absolute pinnacle of human engineering thus far. But exploring all these complex mechanisms inevitably raises an important, overarching question regarding the future.
I figured you would have a lingering thought to leave us with.
Throughout this entire discussion, an underlying theme has been our battle against absolute physical limits. We learned that modern CPUs generate so much localized thermal density that we are forced to employ microscopically conductive pastes and complex liquid plumbing just to keep the silicon from melting. We saw that engineers had to squeeze data transmissions onto both edges of a clock wave because pushing the frequency any higher was physically untenable. And we noted that consumer power supplies are now demanding 1,200 watts of raw power to fuel these ambitions.
We are pushing the physical materials of the periodic table as hard as they can possibly be pushed.
We are rapidly approaching a fundamental wall in physics. A silicon transistor can only get so microscopically small before we encounter quantum tunneling, where electrons simply jump across the closed logic gates unpredictably, destroying the integrity of the data. Copper can only conduct so much heat before it fails to cool the chip, so the question becomes, how long until fans, heat sinks, and liquid loops simply aren't enough to manage the thermodynamics of our insatiable processing demands?
You believe the current architecture is living on borrowed time.
I believe we are standing on the precipice of a necessary paradigm shift. To achieve the next monumental leap in computational power, the computers of the future will likely have to abandon silicon entirely. We briefly discussed how liquid cooling mimics biological cardiovascular systems. Perhaps the true leap forward will be fully biological computing utilizing synthesized DNA strands for incredibly dense data storage and organic enzyme reactions for processing, which generate virtually zero waste heat. Or perhaps we will stabilize quantum computing for mainstream use, utilizing subatomic states that operate at near absolute zero temperatures, bypassing the thermodynamic nightmare of electrical resistance completely.
A desktop computer powered by biological enzymes or contain quantum states.
It sounds purely like science fiction right now, but so did the concept of a multi-core processor demanding 1,200 watts of power inside a home office just 30 years ago. The current architecture of pushing electricity through metal to create heat is reaching its logical climax. The next chapter will have to rewrite the rules of physics entirely. And that is something profoundly fascinating to think about the next time you hear your computer fan spin up.